So we're recording, and I thought I'd review the material on Legendre polynomials because I went through that fairly quickly last time. So let me start at the beginning here. And while I'm at it, let me get rid of the text file and make space for that's one of my grandchildren. Let me make space for the iPad. So I will, let's see, I'm sharing the wrong screen here. No, what screen is being, now I'm confused as to which screen is being shared. So let's see, you are screen sharing. It says here you are screen sharing. I'm not sure what you guys see though. Oh, Lord. So let's. Well, so maybe you can, somebody can say in the chat screen what it is that you guys are seeing, because, all right, I'm going to say new share. So it says I'm screen sharing, but So do you see the mouse? Okay, so I've got the wrong screen up then. So let me switch like this. And put those over there and that over there. Oh, another grandchild, granddaughter in this case. Okay. Yeah, I'm really sorry about all this. So let's see. Let me bring up notes. No, I want to bring up QuickTime Player. Oh, Christ. Well, that may. All right, so, here we go. Okay, now we're more or less where we should be. And I'll just draw a red line across here. And why this is, that's good. Okay, sorry for all that. So let me start again with the Legendre polynomials here. Basically, and just to make sure, where is this chat screen? Damn it. Well, I'll bring it up again, maybe. Chat. Okay, there's the chat screen. All right. Okay, sorry for all this. So Legendre's polynomials. Basically, they're polynomials in X, and they're defined by two conditions. One is that the nth order polynomial is orthogonal on the interval -1 to 1, orthogonal to all polynomials of lesser degree. In other words, Pn of x, x to the m dx from -1 to 1 vanishes if m is less than n. Then the normalization condition is that all the Legendre polynomials at 1 are equal to 1. Then they're unique, and these are the Legendre polynomials. And of course, the plot is that. I'm wondering if I can redo this plot with each polynomial in a different color, but I have not figured out how to, I've not tried to do this or figured out how to do that, but that would, I think, be amusing. Now, Rodrigues invented a formula for the Legendre polynomials, and they're basically the nth derivative of x squared minus 1. Notice x squared minus 1 vanishes at the two ends of the interval -1 to 1. And so that means that all the Legendre polynomials for positive n vanish at the endpoints, but on the other hand, P0 is just equal to 1. And so it is given by just P0 of x is just equal to 1. Okay, so the generating function for the Legendre polynomials is this funny square root. And by a generating function is meant that if you expand in one variable, powers of one variable, you get coefficients that are quite interesting, that are the functions that one is interested in. And you can find out what, you can show that they are the Legendre polynomials by going through this argument here. I think I'm going to skip that. The really important thing is that that this generating function for the Legendre polynomials, which means 1 over this square root is equal to that, is actually the Green's function for Poisson's equation in disguise. And the Green's function for Laplace's equation is 1 over r, big R minus little r. It's like an expression like this. So it's the generating function apart from a constant factor. And in order to see how that comes about, we write, first of all, we get rid of the 4 pi. We write 1 over r minus a big R minus little r like this. And so it is equal to 1 over big R times the generating function.
Dr. Cahill?
Yeah.
We're still not looking at the whiteboard on your shared screen. We're looking at your email inbox.
Oh, God. All right. Thank you. God, I wish you had said so earlier.
Yeah, you got a message on the chat, but I figured you weren't saying that.
Yeah, you figured correctly. Okay.
That's better.
Yeah, thanks very much for that. I guess it's really important for me to start the class in the usual slow way rather than to do it abruptly in a hurry because I lost track of time. Anyway, this Green's function is then a sum of the smaller r over the bigger R raised to the power n times the nth Legendre polynomial in cosine theta. And Legendre's differential equation, well, Rodrigues formula gives us the Legendre polynomial apart from a factor, or it gives it actually gives us exactly the Legendre polynomial, but apart from a factor, it's the nth derivative of this simple it's the nth derivative of u being the nth power of x squared minus 1. And then if we differentiate u once, we see it looks like this. And then if we multiply by x squared minus 1, we repair this minus 1 here, and we get that x squared minus 1 u prime is 2nx x squared minus 1 to the power n, which is 2nxu. So then what we do then is we use Leibniz's rule to to differentiate both sides of this equation n+1 times. And then we get two expressions. For the left-hand side, we get that, and for the right-hand side, we get this. And equating the two, we find after several cancellations that we get the self-adjoint form of Legendre's equation. The Rodrigues's formula can be used to show what the normalization is of the Legendre polynomials, and they're orthogonal, of course, but and the factor is 2 over 2n plus 1. Here's something that I showed you before, namely that one can the completeness of the solutions of the completeness of the eigenfunctions of a self-adjoint differential equation, or at least certainly the Sturm-Liouville type that we've been looking at, tells us that we can write the delta function in as a product of these eigenfunctions evaluated at different arguments. And here we have a weight function that's in fact equal to unity. I often write that as rho. In fact, I should have changed that and set it equal to rho. And so in here we have this 2n plus 1 over 2 normalizes the product of the Legendre polynomials, and the weight function is 1, so the delta function assumes this very simple form. And here's an example choosing x prime equal to 0. And this is a sum of 40,000 terms. Because I chose x prime equal to 0, I could skip all the odd ends. This delta function formula comes from this expression, or equivalently can be used to derive this expression. So if we write f of x as the delta function times f of x prime integrated over x prime, and then we re-express the delta function in this in terms of the Legendre polynomials, we get this expression here. And so this gives us the formulas for the coefficients of f of x if we're expanding in terms of Legendre polynomials. These Legendre polynomials often come up in the case of spherical coordinates, and in that case, we often set cosine theta equal to x, and 1 minus x squared then, of course, is sine squared of theta. d by d theta is d by dx, d cosine theta dx, cosine theta d theta. That, of course, is minus sine theta d by dx. So d by dx then is minus 1 over sine theta d by d theta. And if we then put, I was hoping to get that equation. Anyway, if we substitute d by dx, if we write d by dx as minus 1 over sine theta d by d theta in Legendre's equation, what we get is Legendre's equation written in terms of spherical coordinates. There are various recurrence relations. In fact, there are probably infinitely many recurrence relations that one can derive. I'm not going to go through them. There's one that's particularly useful. If you take the t derivative of the generating function, you get this, and then you can rewrite that in this way. And then you can compare equal powers of t to the n. The coefficients have to be equal in all three cases, all three functions. The coefficient of t to the n in this expression, it must be the same as the coefficient of t to the n in this expression and of t to the n in this expression. You then get the recurrence relation, and the recurrence relation is this. And I think this is what most computer programs that compute the Legendre polynomials use, namely that if they start with p0 equal to 1 and p1 equal to x, they just can zoom up by using this recurrence relation. The special values of Legendre polynomials, well, again, you can use the generating function to show that Pn of minus 1 is minus 1 to the n. That follows from this expression here. G of t and minus 1 is this. That's 1 over 1 plus t. That's just the sum as minus t to the n. Again, here for t within the interval, which only goes from minus 1 to 1. And this then is Pn minus 1 t to the n. So obviously then Pn of minus 1 is minus 1 to the n. If you do g of t, set x equal to 1 instead of minus 1, you then get, you find that Pn of 1 is 1, but that was the original, in the original definition of Legendre polynomials. The generating function is even under the reflection of both variables, and that's because you have a t squared and a tx. So if you set x equal to minus x, t equal to minus t, g of t and x doesn't change. And that lets you write this expression, t to the n p sub n is equal to minus t to the n Pn of minus x. And that then tells you that Pn of minus x is minus 1 to the n Pn of x. And that then tells you that if n is odd and x is 0, that p2n plus, the p odd of 0 is 0. And with more effort, one can show what the even ones are, and one can also show that the Legendre polynomials are also always less than unity in absolute value. I think I'm going to skip the rest of this section and just go to Schlaefli's integral. I think we saw before, we've already seen that Schlaefli wrote the Legendre polynomials as derivatives of x squared minus 1 raised to an integer power, and or rather I should say Rodrigues showed this. Schlaefli then said, well, this is just, we can use Cauchy's integral formula to evaluate that as So what we do is, because it's the nth derivative, we have z minus x to the n plus 1. And because the function is x squared minus 1 to the power n, we have z squared minus 1 to the power n. And the rest of it is 2 to the n, 2 pi I. Orthogonal polynomials. Here, what we see is that Rodrigues's contribution was much greater than just a formula for the Legendre polynomials. What he did was show how to generate families of orthogonal polynomials. And what he did was he said, well, you take some function q that vanishes at the endpoints of the interval. You then take a weight function w, and you construct something like this. The nth orthogonal polynomial is going to be the nth derivative of the weight function times this function q raised to the nth power, and then you divide out the weight function. And then you have a constant en, which is chosen to make the normalization nice. And there are the Jacobi polynomials. Q is x squared minus 1. So that's like the Legendre polynomials. But now the weight function, instead of being unity, is 1 minus x to the alpha, 1 plus x to the beta. And then you get, as the Jacobi polynomials, you get this expression, which is sort of complicated. There's the weight function, then you divide out the weight function. They're orthogonal on the interval when weighted by the weight function, and the actual value of the integral is involves gamma functions. And you have this as the normalization condition, and then they satisfy this differential equation. And there's the generating function is a square root. It's funny, I'm surprised that it's a square root and not an inverse square root. Anyway, so let me just check that. Then I didn't leave out an inverse formula here. In any event, the generating function turns out to be, it is an inverse square root. It's just that I didn't write it initially that way, but we see we divide by r. So we get the Gegenbauer polynomials, Chebyshev polynomials, and finally, when alpha and beta vanish, you get the Legendre polynomials. And you have all sorts of recursion relations. Recursion relations are actually identical, aren't they? Unless I've made a mistake. The Hermite polynomials, these are the ones that occur in the harmonic oscillator for quantum mechanics. There you just choose q equal to 1, and you have a weight function, which is a Gaussian, and then the Rodrigues formula gives you this, and you can rewrite it in this form or equivalently in that form. So you have all these different forms. Anyway, they're orthogonal on the real line and satisfy this, I guess it's called Hermite's differential equation. The generating function, though, is quite different. It's e to the 2xy minus y squared. So that's quite a different generating function from the Legendre polynomials. And of course, the nth excited state of the harmonic oscillator of mass m, angular frequency omega, is hn of x, where x is the square root of m omega over h bar times q. X being dimensionless. The Legendre polynomials, well, here you choose q equal to just x, and the weight function is x to the alpha e to the minus x. And then you have the generalized Legendre polynomials. They're orthogonal on the interval 0 to infinity. And these occur in the radial equation for the hydrogen atom. And you get, they satisfy this differential equation. And here's their generating function. In particular, this the non-relativistic hydrogen atom with quantum numbers n and l, the eigenfunction is proportional to rho to the L, e to the minus rho over 2 times this generalized Legendre polynomial, where here rho is 2r over n a0, a0 being the Bohr radius. Okay, well, we're going through this very quickly. The azimuthally symmetric Laplacians. We saw in section 7.3 that Laplacian separates in spherical coordinates, and if it has no phi dependence, then the solution is just r kl times theta sub L. That'll be a solution of Helmholtz's equation as long as r and theta satisfy this equation for non-negative L. And Legendre's equation, the big theta has a capital theta has to satisfy this equation. This capital theta, though, in this case, I'm not quite sure why I wrote it that way. Anyway, capital theta in this case is just the Legendre polynomial. And for k greater than 0, the solutions of the radial equation, this equation, are the spherical Bessel functions, which, as I said to you before, are very nice functions. They're given by Rayleigh's formula. And so the general azimuthally symmetric solution of the Helmholtz equation that's finite at r equals 0 is given by a sum like this. On the if the origin can be singular, or equivalently, if the origin is not part of the problem, then you can include the Neumann functions, and the spherical Neumann functions are also quite nice functions. They are very much like the spherical Bessel functions, but instead of sine, you have a cosine, and so then you have you have this very nice formula. If k is actually 0, then you get back to Laplace's equation, and then what you have is simply the radial equation is just simply is just very simple, and you can write r to the L as some power of n. And then what you get is differentiating in this way, you get nn plus 1 has to be equal to ll plus 1. And the solutions to that are n can be L or n can be minus L minus 1. And so then we have a sum like this. And if the solution is finite at the origin, then all the b's vanish. But otherwise, you need to conclude all of them. Laplace's equation in 2 dimensions. In section 7.3, we had an example, a rather long example, 7.7, and we saw that Helmholtz's equation separates in cylindrical coordinates, and that the equation for the rho function is Bessel's equation. In cylindrical coordinates, I've said to you before, there's less symmetry, and so the Bessel functions are not as nice as the Bessel functions in the spherical Bessel functions that occur in spherical coordinates. Now, if k equals 0, then Helmholtz's equation, of course, is just Laplace's equation. if there's also no z dependence, then we can just set phi equal to e to the im phi. We don't have any z at all, so the z goes away, and we just have rho of rho and phi of phi, and then the Helmholtz equation reduces to this very simple form, and if the whole range of phi is relevant, then phi must be periodic, and so phi must be an integer. If, on the other hand, and in that case, we just say rho sub m is rho to the n, and we get n squared is equal to m squared, so n is equal to plus or minus m, and then the z-independent solution of Laplace's equation of cylindrical coordinates then takes this rather simple form. So Laplace's equation in 3 dimensions. This, of course, is what you have to solve if you have an electrostatic field in 3-dimensional space with no charges, or you're looking at a gravitational field where there's no matter. You then have the Laplacian of f equal to 0. And what you do, as again we found in example 7.7, is that it's f is r to the L. This capital theta now with 2 indices, L and M, e to the im phi, and theta satisfies the associated Legendre equation. It's called an associated Legendre polynomial, and it's a polynomial in cosine theta and sine theta. And it satisfies this equation. The equation for r sub L, on the other hand, is this equation. And we see once again that n can be L or minus L minus 1. And so then we have as our general solution a sum over L and M of the associated Legendre polynomial, again in cosine and sine of theta, e to the im phi, and then r to the L and r to the minus L minus 1, and you sum over L and M. Of course, this term diverges at spatial infinity. This term diverges at r equal to 0, and so you've got to use different functions in different places. You might, for example, have these functions near the origin, and then you might match them onto these functions at spatial infinity. Helmholtz's equation in spherical coordinates, well, here what you have is minus Laplacian is k squared times f. And again, because we have spherical symmetry, we have these nice Bessel functions, the JLs and the YLs. The JLs being Bessel functions and the YLs being Neumann functions. Theta, once again, if we set e to the im phi, then theta has to satisfy this equation, which is the associated Legendre equation. And the associated Legendre function is a constant multiple of the associated Legendre polynomial. Now, what about these associated Legendre polynomials? Well, what we do, as I said before a couple of times, P sub L super M, which is sometimes written as PLM, both subscripts, they're polynomials in cosine theta and sine theta. And as I said, they arise as solutions of the separated theta equation, which is of the Laplacian and spherical coordinates. It looks like this. So if we go back to X, we then have this as our differential equation. And it turns out that PLM is actually proportional to the nth derivative of the Legendre polynomial. And so we can write it as, in fact, it's proportional to the nth derivative, and the factor of proportionality is 1 minus x squared raised to the power m over 2. And to see why this is the case, what we do is we write the nth derivative of the L polynomial, which is this thing. We write it as PLM time or divided by this thing, which is to say 1 minus x squared to the power minus m over 2. Then if we differentiate this equation, we get this. But now we use Leibniz's rule to differentiate Legendre's equation m times. And so you differentiate this equation m times. Well, partly you get this, you get just PL m, meaning you differentiated this guy m terms, but now you are differentiating these ones, and so you get 1 minus x squared PL to the m plus 2, and then you get some cross terms, and then you get stuff that contributes to this term. Now, so this is the equation that the various derivatives of Legendre polynomials satisfy. If we now take these different expressions for the derivatives and put them into this equation, what we find is that this is actually a solution. So this is so the bottom line is that the associated Legendre functions are the m over 2th power of 1 minus x squared times the mth derivative of the Legendre polynomial. And these then are simple polynomials in x, which is cosine theta, and in sine of theta, which is square root of 1 minus x squared. So another way of writing them is PLM of cosine theta is sine m, or maybe I should have said PLM of theta. Anyway, it's the mth derivative of the Legendre polynomial times the mth power of sine theta. And we can again apply one of the Rodrigues tricks. We already know that PL was an nth derivative of this thing. And now we see that PLM is the mth derivative of that. So we get a Rodrigues-like formula, namely that PLM is proportional to the L plus mth derivative of x squared minus 1 raised to the power L times, and the factor of proportionality is, apart from a constant, it's m powers of sine theta. And now what we see is we have an expression for the associated Legendre polynomial that works for negative values of m, because you see, over here, we can't have negative values of m because we don't, unless we make some imaginative definition of what negative derivatives are, which I'm not excluding. But once we use Rodrigues's formula to express P sub L as an Lth derivative, then we have the L plus mth derivative of x squared minus 1 raised to the power L. Then we can say, well, m can be negative. And in fact, m, how negative can it be? Well, we extend it to negative values of m, and we also learn something else. We learn that under parity, if we let x go to minus x, The x squareds don't change, but we have L plus M derivatives, so we have -1 to the L plus M. And over here, what we see is that this formula makes sense as long as M isn't too negative. M can be -L, and then there's no derivative at all. But M can't be -L minus 1, or we again have negative derivatives, or all right, negative derivatives. On the other hand, if P is greater than L, then we wind up differentiating so much that the associated Legendre function just simply vanishes. And so that's the rule in quantum mechanics, that this quantum number M, the integer M, has to be less than L and greater than -L, or greater than or equal to -L, less than or equal to L. And since M occurs only as M squared, it's not surprising that PL minus M is proportional to PLM. And if M is not equal to 0, there's always a power of square root of 1 minus x squared. So PLM at plus or minus 1 vanish, which means that the Legendre polynomials vanish when theta is 0 or pi, which is to say the associated Legendre functions for M not equal to 0 vanish at the north and south poles. So we have then this ODE here, and this is an interesting ODE because we can think of either LL plus 1 or M squared as the eigenvalue. And if we think of LL plus 1 as the eigenvalue, then the weight function is just unity. And then it's self-adjoint on the interval. And the eigenfunctions are orthogonal. And the orthogonality formula turns out to be this expression here. On the other hand, if we take M squared to be the eigenvalue, then the weight function is 1 over 1 minus x squared. And the eigenfunctions for fixed L and different M must be orthogonal on -1 to 1. And then the formula is this way. So over here, you have fixed M, different L, and down here you have fixed L, different M. And these associated Legendre functions are used to define the spherical harmonics if you combine them, when they're combined with just e to the im phi, which is capital phi of M. So in other words, here, the spherical harmonic is the associated Legendre function, which is just a proportional to the associated Legendre function PLM of cosine theta. So we introduce a -1 to the M and a big square root. And then phi is e to the im phi divided by square root of 2 pi. And then all that together, the product of this times this gives you the spherical harmonic. And the eigenvalue equation then, the eigenvalue equations for phi and PLM imply that the spherical harmonic satisfies this differential equation, and the square root in the definition of the spherical harmonic gives us this very nice formula that if you integrate over all of solid angle, you get that the spherical harmonics are orthogonal. The parity transformation is when you take x and you just go down to -x, you just reflect x, y, and z. But then the radial value doesn't, the radial coordinate doesn't change, but theta goes from, let us say, theta here, it goes down to pi minus theta, and phi goes from, let us say, phi to phi plus or minus pi. And that means that cosine theta gets a minus sign, and e to the im phi. Oh, there's a mistake here. This is supposed to be, let me just fix this. This is obviously e to the im phi. So there's a -1 to the m on the phi, because when you add or subtract pi to phi, you get e to the I pi, which is plus or minus 1. E to the I pi is -1. So m, the phi function gives us a -1 to the m. That cancels the m dependence of PLM. So altogether, under parity, the spherical harmonic changes just by the quantum number L without m. So the parity of an atomic state, which has as its wave function some function of some radial function times a YLM, that's -1 to the L. These spherical harmonics, of course, are complete on the unit sphere, and you can use them to expand any smooth function on the sphere like this. The orthogonality relation is that ALM is just the integral of YLM star times F integrated over the sphere, because remember, the spherical harmonics are orthogonal on the sphere, and the orthogonality relation is delta LL prime, delta MM prime. So you have a very simple relation here. Putting them together, you get F of theta and phi is an integral over the sphere of F of theta prime and phi prime times this sum here. And that tells us that this sum is a delta function, an angular delta function with a factor of 1 over sine theta to cancel this term. And this is sometimes abbreviated this way, delta 2 of omega minus omega prime. The spherical harmonic expansion of the Legendre polynomial of a unit vector, the dot product of two unit vectors, n hat and n hat prime. Hat is often used to denote a unit vector. So the polar vectors of n are theta phi, the polar vectors of n prime are theta prime phi prime. Then this structure here is times 4 pi over 2L plus 1 is the Lth Legendre polynomial. So this is called the addition theorem, and it's worked out in the chapter on group theory. I've got to fix that example thing there. So the cosmic microwave background, this was first, I was first detected actually by some engineers at Bell Labs who were interested in communications, and they wanted to, let's see, I've forgotten what it is they were actually doing. This was back in the early 1960s, maybe 61 or 1960, possibly in the late 50s. Anyway, what they did was they set up a very sensitive radio telescope or a very sensitive antenna, and they were, I suppose they were going to use that to get radio signals from some radio transmitter on the other side of the earth or something. And what they kept getting was static. And they thought that there was something wrong with their electronics. And then they thought, oh, it was that there were birds that were nesting in or around the antenna. So they got rid of the birds and the static was still there. And then it turns out that Bell Labs there was in very close to Princeton, New Jersey. And so the engineers heard that some physicists at Princeton were interested in what they were doing and had an explanation. And the explanation, of course, was that what they were listening to was photons that had been visible. In other words, photons in the EV range, electron volt range, some 380,000 years after the Big Bang, and that they had been traveling then for nearly 14 billion years, and the expansion of the universe had stretched their wavelengths to microwave, so that they were now microwave frequencies and microwave wavelengths, of course. And what they were hearing was they were hearing the radiation from the Big Bang. This radiation was kind of trapped inside the plasma, because the plasma consisted of electrons and protons as well as helium atoms, and the plasma was so hot until about 380,000 years, was so hot until then that the protons couldn't capture the electrons for any length of time, and so any photon, so the photons were, well, the photons were of energies in the electron volt range. So if a hydrogen atom was stable for a second, it would absorb a photon and be ionized by the photon. So the photons were constantly ionizing or scattering off the charges. And the plasma was made up, as I said, of electrons and protons, essentially, and helium atoms. And at earlier times, it was just helium nuclei, alpha particles and electrons, and protons and electrons, and it was just charged particles. But as it cooled down below, I don't know, 10 eV or so, it became mostly hydrogen, mostly protons and hydrogen and helium atoms. Anyway, once eventually the temperature dropped below about an eV, the universe quickly became transparent, quickly on the scale of billions of years, mind you, but it became transparent, and that radiation then is what the engineers at Princeton, at Bell Labs, were hearing. And so since then, the various satellites have been set up to detect this radiation more carefully. The Wilkinson microwave anisotropy probe was one, and then the Planck satellites, and which are at the Lagrange point. This is in the Earth's shadow, about 1.5 million kilometers farther from the sun. Unfortunately, at that distance, the thing is, the satellite is metastable gravitationally, but it's not in the total shadow of the sun, of the Earth, and so it needs a lot of shielding. Anyway, that's that must be where they put the Webb Space Telescope. Also, I can't imagine where else they put it. Actually, anyway, so what does one do? How does one interpret this? This is a map of the CMB, the intensity of the CMB, and it's remarkably constant. It's basically 2.7255 degrees Kelvin, and the difference between the blue regions, which are cool, and the red ones, which are hot, is only about 300 microkelvin. So we're down by factors of 10 to the 4th or 10 to the 5th. anyway, if this is sort of a picture of the whole sky, because you've got 2 pi going this way and or no, you've got pi going this way and 2 pi going that way. And this is the temperature. You can expand the temperature then in terms of the spherical harmonics that we've just been talking about. And the coefficients, we just learned what the coefficients were. You just integrate the complex conjugate of the spherical harmonic times T. And then the average temperature only contributes it to A00, and in fact gives you this 2.7255 Kelvin. The other coefficients give you the difference between the local temperature at that angle minus the average temperature. And then the angular power spectrum is defined as C sub L, where you sum over the m's and take the absolute values. And if the vector n points in the direction theta phi, then this C sub L you can write in this way as the temperature in the n direction, temperature in the n prime direction, and then PL of n prime is what gives you the CL, which is the sum of the absolute values of A LMs squared. And so these can be fitted it's a model. The model is called cold dark matter, or lambda cold dark matter, lambda being a dark energy density, and dark matter being most of the matter in the universe, and L being most of the energy density, lambda being most of the energy density of the universe. And the fit is remarkably good. This is the multipole L of this C sub L right here. And the fact that the fit is so good tells us that that lambda cold dark matter is approximately right, or there's a lot of truth to lambda cold dark matter, but it's got two mysteries in it. What is the dark matter, and what is the lambda? What is this energy density? And so this is these are two huge mysteries. There are two minor mysteries. The minor mysteries are that the prediction of the Hubble constant from lambda cold dark matter and the Planck observations of the CMB, they give a prediction of the Hubble constant. It is 67.7, whereas when the astronomers measure it, they get a value around 72 or so. So that's one problem, which tells you maybe lambda CDM is not the whole story. There's also a matter of something called sigma 8, which is the fluctuations on a scale of 8 megaparsecs. And both of these are errors of 4 or 5 sigma, and so they're significant, but what to make of them, I don't know. It's a curious sociological phenomenon that everybody's focused on these two things: how it is that the Hubble constant is off by a few percent, and how it is that sigma 8 is off by a few percent. Whereas the huge elephant in the room is two elephants in the room, maybe an elephant and a giraffe. And the elephant is, what is dark energy? And the giraffe is, what is dark matter? And the physics community is kind of like magicians. we point, look at this puzzle with the Hubble constant, look at this puzzle with the sigma 8, and that distracts everybody from the much greater mysteries that we're missing out on, namely what's dark energy and what's dark matter. But it's not that we're trying to fake everybody out, it's that we don't know what to do about dark energy and dark matter. And well, people are doing experiments and may discover dark matter in some measurement at some point. If Bill Clinton hadn't killed the SSC back in the 90s, dark matter might have been exhibited 20 years ago. But of course, we don't know what it is. I guess we can start talking since we've got 7 minutes left. Oh, thank you. Matthew Marshall just told me that the James Webb is at L2, so I'm glad I got that right. I can forget things. Bessel functions. I've started the chapter on Bessel functions with the cylindrical Bessel functions, and I really think I should have reversed things, because the spherical Bessel functions are really nice functions, and they're really important functions. I think if there's ever a third edition of this book, I'm going to switch and do spherical Bessel functions first and then the cylindrical ones later. In fact, we could do that now. Why don't I do that now, at least today? So let's go to the spherical Bessel functions, which we've seen several times. You can define them in terms of the cylindrical Bessel functions, but but they're defined in terms of funny cylindrical Bessel functions, namely half integral Bessel functions. So let's just look at the spherical Bessel functions as themselves. The self-adjoint form is this form. X squared JL prime prime plus X squared JL is LL plus 1 JL. This is the eigenvalue. There's this function we call P often, and these occur in the spherical Helmholtz equation, like this. And if we set phi equal to e to the im phi, then the Helmholtz equation looks like this. We divide by v being r theta phi, then we're left with the associated Legendre equation, and the radial equation is this, and the solution of that radial equation is simply the spherical Bessel functions. And Rayleigh gave this lovely formula for the spherical Bessel functions, and you can see why I like them. They're these, I mean, this is a beautiful formula, sine x over x, and you differentiate L times, multiply by x to the L. I mean, you know, what could be nicer than that? By the way, this Lord Rayleigh was actually John William Strutt, so I guess he was happy to be called Lord Rayleigh. Sounds a lot better than John Strutt. Anyway, J0 is sine x over x. J1 is sine x over x squared minus cosine x over x. These are very, very nice functions. And Rayleigh's formula leads to a recursion relation, which is a very simple recursion relation. And you can show from the recursion relation that the Bessel functions satisfy the differential equation. The series expansion, that's the thing that I avoided because I wanted to skip the cylindrical ones. They give a formula for JL sub rho, but on the other hand, you can also get your approximate formula for JL from this formula here. And what you learn is that JL of rho is basically it goes as rho to the L. And physicists doing nuclear physics found that that the scattering was symmetrical when they would scatter protons, say, off nuclei, and apart from neglecting the electromagnetic interaction, they found that it was basically isotropic scattering, largely isotropic, and that meant, what did that mean? That meant that the thing had to be of short range, and so rho had to be very small. And why is that? Well, because if rho is big, what do I want to say? Only the L equals 0 term contributes. And that's because if rho is very small, in other words, super short range, then rho to the 0 is 1. Whereas if you have rho to the if L is, say, 3 and rho is very, very small, you have something that's super small. So the reason that the scattering was isotropic is that the strong interactions, or the nuclear physics interactions, were a very, very short range. And that was one of the first things people learned about nuclear physics. This was back in the 20s or 30s, back when Agatha Christie was writing. By the way, she was a very good writer. So what else? The spherical Bessel functions satisfy, as I said before, this self-adjoint differential equation. You get then the orthogonality. They're orthogonal then. Here, they're orthogonal to, you see, what you've got here is you've got two different things. You've got an L, and then you've got a k squared here, and or rather, you can consider an interval here, 0 to a, and you can put the zeros of the Bessel function here as z. Well, we'll do this next time, and I think I am going to try to invert the sections in this, because it makes sense to consider the spherical Bessel functions, which are really nice functions, rather than the cylindrical Bessel functions, which are nightmare functions. So I'm sorry about the beginning of this thing, that I just was preparing the lecture and just completely lost track of time. I guess then I will stop this and end it, and wish you all a good night, and see you tomorrow at about 5:30 for the 468 class. Remember, all office hours are 4 to 6 on Mondays. We did have one person come yesterday.